Hey, how are you today? Welcome to our next video. This is going to be for assignment 17. It's U-subs day 2. But before we get to U-subs, I really need you to get to this place where you're okay with these questions. F of x equals the integral of 0 to x of f of t dt. Okay? And here's our little graph. Pi over 2, pi over 2, 2 pi, 1, and negative 1. All right, so here's today's question. Where is big F decreasing? A, on 0 to pi. B, on pi over 2 to 3 pi over 2. C, pi to 2 pi. All right, take a moment to think about that. See what you come up with. How'd it go? Do you think you have an answer? Please have an answer. First, what are you looking at? Well, you're looking at not big F. You're looking at little f. But what's little f's relationship to big F? And of course you could say, well, if I integrate little f, I get big F. And yet, for some reason, when a lot of students think that, they say, okay, but they don't understand the implication. So let's dig a little further and say, well, what happens if we take the derivative of both sides with respect to x? On the left side, I'm going to have f prime. On the right side, derivative undoes integral, and I've got little f of x. Okay, so this graph is little f, but it's also big F prime. And if I want to know when a function is decreasing, where do I look? That's right, I look at its derivative. So, what do I need to see on that derivative to know when a function is decreasing? Well, with our f prime sign chart, we would say f is decreasing whenever f prime is negative. So our f prime is negative from pi over 2 to 3 pi over 2, which means f is decreasing from pi over 2 to 3 pi over 2. All right? Well, I hope it's all right. If it's not, you need to be practicing that more and asking more questions. All right, here's a practice one from our last video. Will you please integrate tangent x? Yeah, I don't recognize that derivative either. I know, it doesn't look like a u substitution because there's only one thing there, a function, and no, I don't see its derivative. So it wouldn't surprise me if you were saying, Krupa, what's up here? And then I would say something gentle and useful like, hey, so what if we rewrote tangent as sine over cosine? Now can you use a u-sub? Give it a try. Pause the video, come back when you're done. Okay, here we are. So if you said that u is sine x, yeah, you're going to be going to the unhappy place. So let's get rid of that at the beginning. We know that du dx would be cosine x, and du equals cosine x dx. Okay, so look up here though now. Dx is on top, cosine x is on the bottom, and that's not what this is. Could be pretty sad there. Here's what I mean. Like, if I try and replace dx with du over cosine x, I'm going to have now the integral of sine x over cosine x times du over cosine x. And there's no canceling. There's just this got bigger and scarier. Yeah, not all u's are good. Instead, look in the denominator. Look in the denominator, look inside of a function, look inside of a function in the denominator. Those are going to be my suggestions for you. So our u is cosine x, and our du is negative sine x dx. Or negative du is sine x dx. Here's sine x dx all on the same level. That all gets replaced with negative du. So we've got 1 over cosine x. Oops, sorry, cosine was u. We've got 1 over u times negative du. Well, let's get that negative sign out of the way. 1 over u du. Excellent. Well, we know the antiderivative of 1 over u is ln of u. And don't forget to replace u with that x stuff. Cosine x plus c. Okay, and don't forget these absolute values. All right, so perhaps we're warmed up now. Perhaps we're ready to go. Let's take a look. All right, how about this? The integral of 1 over x squared plus 9 dx. And if it helps, I'll even tell you that u is equal to x over 3. And that never seems to really help people. So what I want to say is, you know, if that were a 1, this would be inverse tangent. So let's turn it into a 1. We'll divide by 9, but at the same time that we're dividing in the denominator by 9, we also need to multiply in the denominator by 9, because then we're not actually changing anything. However, we have brought about a change. 1, that there's this 1/9 out in front now, and 2, 9 over 9 is 1. And now we have a squared thing plus 1, and so we're looking at almost completely inverse tangent. Perhaps we could use this. I wonder what would happen if I squared both sides. I'd get u squared equals x squared over 9. Oh, I have an x squared over 9. That just so happens to be u squared. Now, if someone hadn't given that handy thing to me, I could always know that my u was going to be the square root of this thing, x squared over 9. Yeah. Or I guess I could say that my my u squared is going to be this thing. Yeah. I still don't need, I need to take the derivative. Du dx equals 1/3, du equals 1/3 dx, or dx equals 3 du. So we've got some replacements to make. We're going to put u squared here, and we're going to put 3u here. And don't lose the 1/9 out in front. So we've got 1/9 integral 3 du over u squared plus 1. Wow, that's almost perfect for inverse tangent. I'm going to pull this constant out, and then I will, in fact, have inverse tangent. We'll have 3 over 9 integral 1 over u squared plus 1 du. So that's going to be 1/3 tangent inverse u plus c. Now remember, we need to replace that u with what that u was equal to, and in this problem, that was u over 3. Don't forget the plus c. Okay? All right, so here's yours. It's time for you to step up. And your problem looks like this. 1 over x squared plus 16 dx. Okay. Please find the antiderivative in this situation. Didn't you pause the video? Go pause the video and actually do the problem. Okay, so dividing by 16, multiplying by 1/16, got that 1/16 out in front, 1 over x squared over 16 plus 1 dx. Now I can say that u squared is x squared over 16, or 16u squared equals x squared. Now if I take the derivative of both sides, I'm going to get 4u equals 2x dx. That's not what I wanted. Oh, isn't that interesting? And here I had hoped it would work. So I have to do this with u. Oh, wait, maybe I just forgot it. Okay, let me try again. X squared over 16. The derivative here, there we go, 2u du dx equals 2x over 16. Okay. I can do a bunch of stuff here. I can multiply both sides by dx. So those cancel. I can divide both sides by 2. Okay, u du equals x over 16 dx. Yeah, no, I don't like that as much as what I had been doing. Well, I guess I'm going back to what I had been doing. Take the square root of this and say that u is the square root of that. Okay, so then du dx is 1/4, or du equals 1/4 dx, or 4 du equals dx. So I can get rid of that with 4 du. And I can get rid of that by squaring both sides. U squared is going to be x squared over 16. There's x squared over 16, so that's equal to u squared. Don't lose that 1/16 up in front. Got that 1/16 out in front. We've got 1 over u squared plus 1. And what was dx? Dx was 4 du. Okay. Migrate that constant out in front. 4 over 16 is going to be 1/4. And the integral of 1 over u squared plus 1 is tangent inverse u plus c. Don't forget to back sub your u in. So we really want to see that. 1/4 tangent inverse x over 4 plus c. That 4 is inside the inverse tangent. That 4 is not. Okay. So let's do some more. How about this one? Integral y over y squared plus 25 dy. What can we do here? By the way, I'm not actually thinking that this is going to be inverse tangent. I know it looks very similar. 1 over y squared plus 25 would be inverse tangent, but this one, no. It is a u sub, yes, because look, I see a function, and I see part of the derivative of that function. So I'm going to say my u is y squared plus 25. So I take the derivative of both sides, I get 1 equals 2y du dx. Du dx, no x's. Maybe du dy, but no. Okay, this is du dy. Yeah, that's not reading right to me. Okay. So what if y equals x squared plus 25? Then we took the derivative and we would have dy dx. So that's du dy over there. Du dy equals 2y. And if we multiply both sides by dy, du is 2y dy. Well, I see a y dy, so if I divide both sides by 2, I can do that substitution. Y dy is equal to du over 2. And this stuff down here on the bottom, y squared plus 25 is our u. So this becomes 1 over u du over 2. We can pull that 2 out. Whose derivative is that? I need you to be able to say ln of u's derivative. And what's u equal to? There's our u. 1/2 ln y squared plus 25. So why did I not worry about absolute value here? Well, y squared plus 25 is always going to poop out a positive. Right? Think about the graph. Shifted up 25 places, up pointing parabola. And so, yeah, that's never going to be negative. That's never going to be 0 with real numbers. And so we don't need absolute value. Yes, you can use absolute value. There's no problem with that. Okay. Next. What about this one? 1 over y plus 25 dy. How do we do this one? Well, I see a function and its derivative. So y plus 25 equals my u. So I'm going to have du dy equals 1. Or dy equals du. So I can replace that with du, and I can replace that with u. 1 over u du. So my antiderivative simply ln u plus c. And let's now plug our u back in. ln of y plus 25 plus c. Notice I'm back to absolute value bars because this can be negative. Okay, so, just like every time we see something that looks kind of like inverse tangent, not all things are inverse tangent. The last two problems have been ln. Oh, by the way, not everything in a denominator is going to be an ln. So really, you can't make that classification. Please don't make that classification. If it's in the denominator, you're going to have an ln. Yeah. So there are lots of different sort of things that we can have in denominators. How about this one? How about the integral of 1 over, I wanted the integral of y squared over y squared plus 25 dy. Yeah, so what is it that we do here? Well, when the degree of the top is the same or larger than the degree of the bottom, we learned last year, maybe the year before, that no, I don't think so. This is improper when the degrees are the same or the one on top is bigger. And what we're supposed to do in that situation is some long division. I know, right? So we've got y squared plus 0y plus 0. What do I multiply that by to turn it into that? 1. Y squared plus 25. And subtract. So we get negative 25 because we were subtracting over y squared plus 25. Now, how does that help me, Mr. Kukla? No worries, here it comes. I can't integrate that, but if I do long division and turn it into that, well, now I can have two integrals. That one minus that one. Pull out that constant, and yes, this is inverse tan. Divide by 25. Multiply by 25 in the denominator. Look, these are going to cancel. So what are we going to have? Well, I'm going to have the antiderivative here is y. We've got minus the integral 1 over y squared over 25 plus 1 dy. Don't forget the square root of top and bottom is your u. And we know that if we take the derivative here, du dy equals 1/5. And if we multiply both sides by dy, and maybe multiply both sides by 5, I get that 5 du equals dy. So I can replace that with this. I can replace that with this being squared. So, okay, where are we now? Y minus integral 1 over u squared plus 1, 5 du. I'm going to pull the constant out. Y minus 5 integral 1 over u squared plus 1 du. And that's going to bring me 5 tangent inverse of u plus c, or y minus 5 tangent inverse of y over 5 plus c. There you go. Long division. Kind of exciting, huh? And filled with terror. Okay, but wait, that one could also be confused with this one, the integral of y squared minus 25. So, you know, the funny thing is, I'm not going to do inverse tangent here, because inverse tangent requires that to be a plus. And I'm not going to do a u sub where this denominator is my u, because I don't see a 2y anywhere, or even a y, an extra y floating around. So what am I going to do? Well, you're going to love this. Partial fraction decomposition. That's what we need to do here. Partial fraction decomposition. So we're going to take this y squared minus 25 and turn it into y minus 5, y plus 5. We'll do our partial fraction decomposition setup for non-repeated linear functions. And now let's multiply both sides of this equation by y minus 5, y plus 5. And so we're going to have 1 equals a y plus 5 plus b y minus 5. Okay. Hey, if you don't have any clue what I'm talking about here, it may be worth your time to go watch the partial fraction decomposition videos. I think there's 2 or 3 of them in my pre-cal channel. Okay. All right. Oh, and if you do, I believe the unit is called graphing rationals and partial fraction decomposition. So that's what you'd be looking for. Okay. So how do we solve this? Well, I like using magic numbers here. How about y equals -5? If I plug in a -5 for y, this becomes 0. 0 times a, that goes away. If I plug in a -5 here, I get -5 minus 5 is -10. 1 equals -10b, and b equals -1/10. Now, what if instead of plugging in y equals -5, we plug in y equals +5? Well, 5 minus 5 is 0. 0 times b makes that disappear. 5 plus 5 is 10a. 10a equals what? a equals 1/10. And we should know that while this time they came out to be opposites, they often have no relationship with each other. So don't try and say in your head, these values are always opposites or the same, because no, that's not true, and just do the partial fraction decomposition. So here's what I understand. This thing that I wasn't sure how to integrate can now be rewritten as the integral of 1/10 y minus 5 plus negative 1/10 y plus 5. And that'll be dy. All right, well, the first thing I want to do is pull out these fractions because they're constants. So I'm going to pull out a 1/10. And I'm going to have 1 over y minus 5 minus 1 over y plus 5. And I've got a dy here. So this would be the moment in time when I would think about a u sub. Like here, I can say that u is equal to y minus 5. And that du equals dy. And so I've got 1/10 integral 1 over u to u minus, and I could do the same thing here, u equals y plus 5, du equals dy, and so we've got 1 over u, and that's a du. So here, I'm going to have ln of this u minus ln of this u. And don't forget we have this 1/10 out in front. Now, of course, two logs joined with subtraction. I could condense that. This could be 1/10 ln y minus 5 y plus 5 plus c. In fact, you could even kick that up there and say that ln y minus 5 y plus 5 to the 1/10 power plus c was our antiderivative. Now, I might expect to see this on multiple choice. This would certainly be fine for free response, but I want to give you some permission to breathe. Partial fraction decomposition is not required on the College Board AP Calculus AB exam. This is actually, this partial fraction decomposition is part of Calc 2. And so if you were taking BC Calc, you would definitely need to do this. But mostly what I wanted to try and get you to see was that we've got lots of things that look similar to each other. To review, 1 over x squared plus 1 dx, that's going to be inverse tangent. And we had a variation on that, I think something like y squared plus 16 dy. This is also inverse tangent. I think it was 1/4 tangent inverse x over y over 4 plus c. Okay, but then we also had 1 over y squared plus 16. Same as that. And we had y over y squared plus 16. And remember, this was a u sub where y squared plus 16, all the stuff in the denominator, was my u. And so my du would be 2y dy. But I only see a y here, so du over 2 equals y dy. And so all of that can be replaced with that. So this is a different kind of u substitution. Then we saw the case where we had the integral of y squared over y squared plus 25 dy. This one was long division. When do I look for long division? When the degree of the numerator equals or is greater than the degree of the denominator. And here the degrees were the same, so I used long division. And then we just looked at 1 over y squared minus 25 dy. And this turned out to be partial fraction decomposition. And ideally, when you work on your integration packet, your differentiation integration packet with those 300 some odd problems, you keep practicing this because you don't want to really waste a lot of time on the test not being sure what method to use. And the only way to get there, boys and girls, is to practice as many as you can. I mean, really get comfortable with this. So we've got this one versus this one versus this one versus this one. Look, they all look similar. They're different. What's that one? That's right. ln of x plus c. This one, well, that's the same as x to the minus 2. So I'm going to add 1 to that power. Now, if I took the derivative of this, a negative would come down, and I don't see a negative there. So there must be something present in the original so that when I take its derivative, I end up with that. So there's that one. This one is a u sub, where x plus 1 is our u. So we end up with 1 over u du, which is the ln of u plus c, or ln x plus 1 plus c. And there's our dear friend inverse tan. This one is tangent inverse of x plus c. We've got to get comfortable with these. You should really practice. Yeah. And if you can't find enough practice, let me know. I'll be happy to help you. Okay, so let's take a look at this. The integral of cosine squared x sine x dx. Okay, what can we do here? Well, I actually think it's a u sub because I see a function inside of another function, and I see the derivative of that inverse function. Well, or at least part of that derivative. It may help for you to rewrite this slightly. That's the same thing. Inside the squaring, outside. I see a function and most of its derivative. So I'm going to say that u equals cosine x, and therefore du is negative sine x dx. Okay, so negative du is sine x dx. They're all on the same level. They're all on the same level. So I can rewrite this integral as u squared times negative du. And so I don't get confused, I'm going to pull that negative out in front. Okay, what's the antiderivative of u squared? Well, that would be u to the third over 3. Don't lose the minus, don't lose the c, but do plug in that u. So our antiderivative is going to be cosine to the third over 3, the minus in front, and a plus c in back. Well, that seemed pretty doable. Or at least if I practice my u subs a little more, it should be pretty doable. But what if this one? It's very similar. Remember, our last one was cosine squared x sine x dx. Okay, that was the last one. This one, cosine squared x dx. Yeah, so here's the thing. Yes, cosine is the inside function, but no, I don't see that derivative of cosine like I did in the last problem. Okay? So there was something that we talked about last spring in trig. There's something that we talked about again when we were doing a trig review at the beginning of this year. And that is that you were going to get to a place where you were pretty desperate because you couldn't do it any other way. Well, this is that place. When I see cosine squared by itself, or for that matter, sine squared by itself, I need to use my power reducing identities. It's why we reviewed them in trig. It's why we reviewed them back in August when we were doing our trig review. I know you've forgotten them, but guess what? Yeah, you can't do that. So cosine squared, well, I know that cosine squared is the same as 1 plus cosine 2x all over 2. How is this going to help? Well, check it out. I'm going to replace cosine squared with this power reducing identity. See how the power was 2 and now the power was 1? Oh, but yes, that's true. The angle doubled. And that always happens. So what do I have here? I've got 1 plus cosine 2x all over 2. Or, here's the dx. Or, bring out that constant. 1 plus cosine 2x dx. Well, that seems almost reasonable. This could be 1/2 the integral of 1 dx plus the integral cosine 2x dx. In this situation, I know the antiderivative of 1 dx is going to be just x. So I'm going to have 1/2 x. Over here, I like to do a little u sub. U equals 2x. So du over 2 will be dx. So that's my u, and that's du over 2. And I'm going to bring that 2 out here with this one. So what's that going to look like? Well, here we've got that 1/2 x plus 1/2. The antiderivative of cosine is sine of u times du over 2. This guy comes over here, and we've got 1/2 x plus 1/4 sine. I skipped a step, didn't I? Sorry, let me go back and do it right. There's an integral there. There's du over 2 here. Let's bring that out. And so now we've got 1/2 x plus 1/4. The integral of this was cosine. Okay, and cosine u du. We know the antiderivative of cosine is sine of u. And finally, what was u equal to? 2x. See? 2x. There we go. My ability to get there without a power reducing identity? Almost nil. So when do I need to use power reducing identity? So if you see sine squared x dx or cosine squared x dx, if you see either of these, must use power reducing. So remember that sine squared is 1 minus cosine 2x over 2, and cosine squared is 1 plus cosine 2x over 2. I have to replace that thing that I can't integrate with some stuff I could break into 2 fractions and integrate. Now, we saw in the problem directly prior to this that the integral of cosine squared x sine x dx was just a plain old u sub, where u was cosine x. It's when I have cosine squared or sine squared alone, no friends. Friend, maybe u sub. No friends? Power reducing identity. Okay, so I need you to be comfortable with power reducing identities. All right, well, let's see what you know. How about this one? The integral of sine squared 2x dx. Would you please find the antiderivative there? Or evaluate this indefinite integral? Pause the video, give it a try. Okay, welcome back. So I hope that you took u for your 2x. And du is 2dx. Okay. I guess you could say that dx is du over 2. Now, we see the sine squared, and we know that sine squared theta is 1 minus cosine 2 theta over 2. So what's my theta? This is my theta. So that has to go in there. 2 times theta. 2 times this. So I'm now going to have integral 1 minus cosine 2 times 2x, 4x, all over 2. And we've got dx here. Okay, well, let's pull out that constant. 1 minus cosine 4x. 4x dx. Okay. So, my u, I would make 4x. And u over 4 is dx. So I can replace this with that stuff. And I can replace this with u. So, how can we do this? Well, I like splitting this up into 2 separate integrals. And replacing this 4x with my u, and replacing dx with du over 4. So we should now have the integral here is going to be 1/2 x minus 1/2. The antiderivative of cosine, well, I guess you wanted me to write it as a u first, didn't you? Cosine u du over 4. Okay. Let's pull that constant out. We'll have 1/2 x, 4 times 2, 1/8, integral cosine u du. We know the antiderivative of cosine is sine u. Don't forget the plus c. This is 1 over 8. And we have 1/2 x here. Plug that u back in. 1/2 x minus 1/8 sine 4x plus c. And there we go. Yeah, you are expected to do that. Might be good to watch this video again. Might be good to pause the video and practice some of these. How about this one? The integral of cosecant squared x dx. What can we do here? Yeah, that's right. We should recognize that as someone's derivative, or at least most of someone's derivative. Remember, if y equals cotangent x, then y prime is negative cosecant squared x. So, I can replace, well, I don't have to replace, I can just say, hey, I know that your derivative is this, and I'm just missing that minus. So I think I've got minus cotangent x plus c. Let's think about that. If I take the derivative of minus cotangent, I'm going to have minus a minus cosecant squared x. Hey, I've got minus a minus cosecant squared x here. There's my antiderivative. Wow, it's almost like all this math from the last few years is showing up right now. Whether it's long division, or partial fraction decomposition, or power reducing identities, or just knowing my trig derivatives, it's all showing up here. Okay, I got 2 more that I want to do with you. How about this one? Cotangent squared x dx. We saw in the last problem that cosecant squared problem, I recognize that derivative. But what about this one? Some students want to do it as cosine squared over sine squared. Yeah, that squaring thing, that really sucks there. You really don't want to do that. And no, this isn't a derivative we recognize. But what I can do here is just hate this. Remember how sine squared plus cosine squared equals 1? And if we divide everywhere by sine squared, we could write this as 1 plus cotangent squared equals cosecant squared. Well, if I subtract 1 from both sides, I get that cotangent squared is cosecant squared minus 1. And that's what I'm going to replace. Cosecant squared x minus 1 dx. How does this help me? Well, let's split that into two integrals. We've got cosecant squared x dx minus 1 dx. Hey, look, that was our last problem. So what do we know about this? We know that that is going to be negative cotangent x, and here minus x. The antiderivative of 1 with respect to x is x. Don't forget the plus c. Well, wasn't that unexpected? So yes, guess what we also did in trig? We said that your Pythagorean identities were terribly, terribly important. Not just in their original form, but also that you needed to be able to recognize that cotangent squared was cosecant squared minus 1. No kidding. They really expect you to remember this. So you really do need your identities. When we reviewed them in August, there was a reason for that. You get here, and I can't integrate that without using my Pythagorean identity. Okay? All right, last one. How about this one? Integral of cotangent x dx. And I'll give you a hint. It's a u sub. And it looks a lot like a problem that we did at the beginning of class. I know. Isn't that really interesting? So, what do we have here then? Well, this is going to be cosine x over sine x dx. Can you go from here? If you can, pause the video, give it a go. For me, I know my u is sine x. It's that thing on the bottom. du is cosine x dx. Oh look, the whole top is my du. And so I can rewrite this as 1 over sine u, 1 over u, there we go, 1 over u du. And that's just going to be ln of u plus c. And here's our u. So we want ln of sine x plus c. Don't box your answer. There's mine. All right. Well, I hope that you both are getting a little practice and a little more comfort with u subs, but that you're also becoming keenly, keenly aware that so many things look similar. So let's go. ln negative x to the negative 1, ln inverse tangent. This is, what is that one? That's, I want to say that that's secant. Do we know that secant is the derivative of something? Oh, I think this is by parts. Yeah, we'll be doing that in the very near future. Cosine squared times a sine, that's a u sub. Cosine squared by itself, or sine squared by itself, you've got to use power reducing. Hey, look, a sine squared by itself. Oh, there's something on the inside. That inside could be my u for a u sub, but I also have to use power reducing identities here. Here, cosecant squared, I'm supposed to recognize that as the derivative of negative cotangent. And here, where we had cotangent squared, this one then, we needed our Pythagorean theorem, our Pythagorean identities, to do a replacement there. And finally, cotangent by itself, we thought about cosine over sine and chose the bottom for our u. Look here at the top, u sub. This is inverse tan, but the u sub has y over 5. This one was long division, and this one was partial fraction decomposition. So, yeah, you've got to practice this stuff. Okay, love you. See you in the next video.